By the year 2026, large-scale enterprise operations moved far beyond simple conversational chatbots and integrated fully autonomous agentic workflows. But the data from these early deployments reveals a difficult reality. 95% of generative AI pilots fail in real-world environments, often due to operational chaos and spiraling costs. These failures trace back to a specific architectural flaw. Engineers are asking large language models to ingest instructions, plan a solution, and execute massive multi-step operations, all within a single monolithic prompt. If you ask a master chef to cook a 5-course meal, they don't throw every ingredient into one pot and hope for the best. They build a prep timeline. They map out their dependencies. This transition toward reliability is centered on a specific functional division. To move beyond these fragile prototypes, modern developers are beginning to separate the overarching plan from the individual steps of execution. When an AI agent tackles an exploratory task, the exact sequence of necessary steps isn't always clear from the start. The agent has to determine the path as it progresses. This React flowchart forces the agent to systematically navigate uncertainty. First, it analyzes its current state to declare which tool to call next. Then it executes that specific tool. Crucially, it enters an observation phase to inspect the real-world output before taking further steps. Forcing this deliberate, step-by-step observation prevents the model from hallucinating a string of actions and rushing down an unrecoverable path. Exploratory loops are effective for research, but complex deterministic operations require a much more rigid architectural framework. In Plan, Execute, Replan, a planner plots subtasks into a dependency graph. Locks secure prerequisite steps. Downstream actions physically cannot trigger until higher nodes complete. If a step fails, an evaluator flags the error, kicking the workflow back to generate a secondary path. Drafting an explicit, verifiable roadmap prior to execution provides a reliable way to manage extreme complexity without the core model losing its context. Running a massive dependency graph sequentially can create a speed bottleneck. Waiting for one step to finish before starting another often wastes available compute. When mapped subtasks are independent of one another, the architecture shifts to parallel delegation. A master planner distributes the work simultaneously to distinct worker nodes. Uber applied this parallel architecture via the Figma console to automate the generation of their software design specifications. By dispatching the design analysis to multiple agents concurrently, they condensed a manual documentation process that typically takes weeks into a matter of minutes. Achieving that level of speed is only possible because a single planner coordinates the workload across multiple autonomous executors. But speed is only half the equation. This same architecture is what solves the original problem of operational chaos. By fracturing a massive goal into isolated subtasks, you interrupt the cascade of compounding errors. Instead of one mistake poisoning the entire output, failures are trapped within specific branches. The Replik case study provides evidence of this efficiency. Their coding agent utilized these planning structures to reach a first-try deployment success rate of 92%. If you want your agentic workflows to survive in production, you must separate your planners from your executors.